Imagine a world where time isn't constant, where space can bend, where energy and matter are two forms of the same thing. This isn't science fiction, it's our reality, unveiled by one of the greatest minds in history, Albert Einstein. His theory of relativity didn't just change physics, it revolutionized our understanding of the universe itself. Before Einstein, Newton's laws seemed to explain everything. The universe was like a giant clockwork machine, but there were cracks in this perfect picture. Einstein saw these cracks and realized they were windows to a deeper truth. His theory wasn't just a small update, it was a complete overhaul. It challenged our basic assumptions about space, time, and gravity, and it all started with a simple question: what if the speed of light is constant for everyone? This question led to ideas that seem impossible at first glance: time dilation, length contraction, and the equivalence of mass and energy. These concepts shape our world in ways we're only beginning to understand. Think about space and time for a moment. They seem like completely separate things, right? Space is where stuff happens. Time is when it happens. Simple. But Einstein showed us that this simple view is wrong. Space and time are actually two aspects of a single thing, space-time. They're woven together like threads in a fabric. This idea of space-time is key to understanding relativity. In our everyday lives, we don't notice it, we move too slowly, and the gravity around us is too weak. But when things move very fast or when gravity gets very strong, the effects become clear. Time can slow down, space can stretch or compress. These aren't just mathematical tricks, they're real effects that we can measure. Massive objects like stars and planets curve space-time around them. This curvature is what we experience as gravity. It's the shape of space-time itself guiding how things move. Let's dive into the first part of Einstein's theory, special relativity. It deals with objects moving at constant speeds. The special part is that it doesn't include gravity, but don't let that fool you. Its implications are anything but ordinary. At its heart are two simple ideas. First, the laws of physics are the same for everyone. Second, the speed of light is constant for all observers. These simple ideas lead to some wild conclusions. As objects move faster, time slows down for them. This isn't just theory, we've measured it. Astronauts on the International Space Station age slightly slower than people on Earth. Imagine if you could travel at nearly the speed of light. You might return from a journey to find that centuries have passed on Earth. Length changes too. As objects move faster, they get shorter in the direction of motion. This effect is called length contraction. Perhaps the most famous part of special relativity is the equation E equals mc squared. A tiny amount of mass can be converted into an enormous amount of energy. Section 4. General relativity, gravity's new face. Now let's turn to the second part of Einstein's theory, general relativity. This is where things get really wild. General relativity explains gravity in a completely new way. It's not a force pulling on objects. It's the curvature of space-time itself. Massive objects like stars and planets bend the fabric of space-time around them. Other objects then follow the curves. Imagine rolling a marble on a stretched rubber sheet. Now put a heavy ball in the center. The sheet curves, and the marble follows the curve. That's a simplified two-dimensional version of how gravity works in three-dimensional space plus time. This new view of gravity explains things Newton's theory couldn't, like why light bends around massive objects, or why Mercury's orbit doesn't quite match what Newton predicted. General relativity makes some startling predictions. It says that extremely massive objects can curve space-time so much that even light can't escape. We call these objects black holes. Section 5. From Theory to Reality, How Relativity Shapes Our World. Einstein's theories might seem abstract, but they have very real impacts on our daily lives. Take GPS, for example. Without accounting for both special and general relativity, GPS wouldn't work. The atomic clocks on GPS satellites run slightly faster than clocks on Earth. If we didn't correct for this, your location would be off by miles within a single day. Relativity isn't just for satellites, it's crucial in particle accelerators too. These massive machines smash particles together at nearly the speed of light. Without accounting for relativistic effects, they simply wouldn't work. The Large Hadron Collider, which discovered the Higgs boson, relies heavily on Einstein's theories. Section 6. A new lens on the universe. The legacy of Einstein's ideas. Einstein's theories didn't just change physics, they changed how we see ourselves and our place in the cosmos. They showed us that our common sense views of space and time are just approximations. The true nature of reality is far stranger and more wonderful than we imagined. Relativity opened up new questions too. If space-time can ripple, can we detect those ripples? In 2015 we did. We detected gravitational waves for the first time. These are ripples in space-time caused by massive cosmic events like black holes colliding. It's like hearing the universe for the first time. A whole new way of observing the cosmos. Einstein's ideas continue to inspire new research. Scientists are still testing the limits of relativity. They're looking for places where it might break down, because we know it must, at some level.